Okay, students. So today we are going to solve this question. Let's read this question. A long straight wire carries current I. A particle having a positive charge q and mass m kept at a distance x naught from the wire is projected towards it. Projected towards it. Oh, okay. I didn't notice that. With a speed v. Find the minimum separation between the wire and the particle. Now, it's not that simple. This question is a little more challenging because magnetic field is not uniform, obviously. So let's start this. So let's say here we have this wire, which is carrying some current I. All right, see, a straight wire carries current I. We all know that this wire is going to produce a magnetic field into the plane, on this side into the plane, and the value of this magnetic field is going to be mu naught I upon 2 pi r, because it's an infinitely long wire. Okay, when they say long straight wire, it automatically means infinitely long wire. Now, this field is not uniform because, as you can see, it depends on the distance r. Okay, so motion of a charged particle in a uniform field we have studied. If the field is uniform, then we know there are only three types of motion possible. If the magnetic field is uniform, we know there are only three types of motions possible. Either it will be a straight line motion, or it will be a circular motion, or it will be a helical motion. But this is not same. This is not at all same, because here magnetic field is not uniform. So as I said, it's not going to be that easy. Anyway, so a long straight wire carries current I, particle having a charge q and mass m. So let's say there is a particle over here which has charge q and mass m, and it is projected, and it is at a distance x naught from the this wire. So right now it is at a distance x naught from this wire. Okay, and it is projected towards it. So this is being given a velocity in this direction towards it, something like this. So this is the velocity vector. Just a sec. This is the velocity vector. So clearly it's going to experience a magnetic field force as per the formula. FB vector is equal to v cross b. And if you do v cross b with your right hand rule, this is your v, and this magnetic field is into the plane because current is flowing this way. So magnetic field on this side is going to be into the plane. If you do v cross b, you are going to get in this direction. Okay, this is v cross b. So this is going to be the direction of the force. So this is your velocity vector. This is magnetic field, and this will be the direction of the magnetic force. Because of it, it will tend to move like this. Now again, I'm telling you, it's not a circle. Don't think it's a circle. It would have been a circle if magnetic field was uniform. So here it starts moving like this. Now it says find the minimum separation, okay, between the wire and the particle. So when the separation is minimum, I think one thing we can clearly notice, for example, right now here the speed is going to be like this. So one more thing, the speed is not going to increase or decrease. You know, the magnetic field can't do any work. So in a pure magnetic field, whether it is uniform or non-uniform, as long as there is a pure magnetic field and there is no other field like electric or gravitational field, as long as there is a pure magnetic field, kinetic energy has to remain constant, and hence speed has to remain constant. So this velocity is neither going to increase nor decrease, only direction is going to change. Although it won't be a pure circle, it will be some kind of curvilinear path. Now the thing is, okay, you have to find the minimum separation. So right now, if the velocity is in this direction, okay, that automatically means that it's going to move. It's going to move closer to the wire. So that means it is going to come closer to the wire. But it is saying that we have to find the minimum separation. So I think when it is at the minimum separation, the velocity of this body must be somewhere like this. Why? Because because only in this case, you see, this velocity doesn't have any component. This velocity right now doesn't have any component in this direction. That means right now, whatever is the separation between these two, between the wire and this, that separation has to be the minimum separation. I'm going to call it xm. So you have to find the value of this xm. So how to go about it? Whew. Yeah. So we have to consider a general time. Let's say it's going to be a two-dimensional motion. It's not a 3D motion. So whatever will be the motion, it will be confined in this xy plane. Let's call this axis as x-axis and this axis as y-axis. So its motion is confined in this plane. So at a general time t, let's say this is the velocity v, and we are going to resolve this velocity to two components. Let's call it vx and vy. Okay, let's call it vx vector and vy vector. Now at this moment, it's going to experience magnetic force. Again, as per v cross b, it's going to experience magnetic force in this direction. Just a sec. It's going to experience magnetic force in this direction as per the formula. So this is going to be the magnetic force. There will be a lot of mathematics involved, I think. Okay, this velocity, let me bring it here. Just a sec. Yep. Okay, why am I calling it vector? It's fine, we can call it, but since it's a result thing, better not to call it. Anyway, so I'm going to say, okay, let at a general time t, okay, I'm not going to write all those things. Okay, at a general time t, let the velocity, okay, at least I should write general time t. So at a general time t, let's say the velocity is something I cap and plus something j cap. Now what will be the magnetic force at this moment? So FB vector at this moment is going to be what? QV cross B. Now QV vector we have just now assumed Vx I cap plus Vy j cap. Yeah. cross b vector. Now b vector, as you know, it's given by this. So at a general time t, let this distance be x. I mean, that also I should have said, okay, let this distance be x at a general time t. Let this distance be x. So at a general time t, this magnetic field is going to be mu naught I by 2 pi x, and direction is going to be minus k cap. Because you know, if you call this as x and this as y, then z axis has to be out of the plane, because x cross y should give you z, and this magnetic field is into the plane, so I'm going to call it this minus k cap. Now let's do this cross product. So these things, mu naught I by 2 pi and x also I'm going to bring outside. So q mu naught I means this I, here I've used small letter, so better I should use small letter. Mu naught I by 2 pi, and even x I'm bringing outside, although I think I'll write 1 by x like this. And then let's do v, yep, I cross minus k, I cross minus k. Now you know very well that I j k, we write something like this, and to do cross product we move like this in anti-clockwise fashion. So we have to do I cross k, I cross k, that means we are moving in this direction, so it will be minus j cap. So you'll get vx minus j cap, fine. And then vy cross this, so j cross minus k, j cross k, we are moving in the direction of the arrow, so it will be I cap, but already we have this minus sign. Okay, I sorry, here there will be plus sign because of this minus. Anyway, I'll repeat it again, not a problem. I think this is simple enough. So I'll repeat it again. See, I'm doing I cross minus k over here, I cross minus k. So I cross k is minus j, but then there is one more minus sign over here which will make it plus. So this part is done. Now this part, so I'm doing j cross minus k. So j cross k, we are moving in the direction of the arrow, so it should be I. Yes, so j cross k is I, and there is a minus sign. So too many mistakes I have done. Fine. So here there will be a minus I cap. Yep. So this is your force. Okay. So what will be acceleration? You know, acceleration vector is nothing but force vector divided by mass. Now the only force here acting is Fb. So one more thing. This one. Okay. Just a second. So q mu naught I by 2 pi, and then m will be there because we are dividing it by m. This into 1 by x. I'm deliberately not. I'm not putting x inside because x is a variable. See, x is this distance. This distance. It's going to vary. And then I'll write the I cap component first, because you know normally when we write a vector we write I cap and then j cap and then k cap. Normally this is what we do. So minus vy I cap and plus vx j cap. Okay. Now we'll have to write this all the time. So what I'll do is I'm going to call it some. I'm going to give it some name. Let's call it some lambda or something, because so many times we have to write it. So from here we can get x component of the acceleration is this lambda into this, because this I cap means x component. So we are getting minus lambda vy by x. Okay, and y component of this acceleration, y component means j cap component, so this lambda 1 by x and vx. So we get lambda vx by x. So this is what we have got. So till now we achieved this, but there is a lot of work to be done now. All right, see, what do we want? Let's go back to the diagram. We want this minimum distance. Also we know that at the moment this distance is minimum. Okay, velocity is going to be purely vertical. I mean, I shouldn't say vertical, but it should be purely along y-axis. All right, that means the x component should be 0. So somehow that condition we have to use in order to find the minimum separation. Huh? Yeah. So where I was? Yes, I was saying that somehow we have to make use of this condition, that at the time of the minimum separation, the x component of the velocity, which means vx, is going to be 0. Now what to do? I can write ax as dvx by dt. Okay, and similarly I can write ay as dvy by dt, but I don't want to bring dt into consideration, because this question is not saying to ask time, to find time and all that. Okay, so instead of that I'm going to use this relation. You know, acceleration can also be written as v dv by ds. S is for displacement. Okay, I'm going to use it 2 times, once along x-axis and once along y-axis. So this one I'm going to write vx dvx by dx. You know, v dv by ds. Now because we are using it only along x-axis, so we can say vx dvx by dx is equal to minus lambda vy by x. And similarly here, vy dvy by dy is lambda, here minus sign is not there, I hope, into vx by x. Now notice one thing, this is a differential equation in vx, but on this side we have vy. I mean, just imagine how beautiful it would have been if there was vx over here. Okay, then I could have cancelled this, and then it will be a pure differential equation purely in terms of vx, x and x, but unfortunately that's not the situation. Similarly on this side, this is a differential equation in vy, This is a differential equation on Vy, but unfortunately here we have Vx. Okay, again, if instead of Vx, if here we had Vy instead of Vx, if here we had Vy, then again we could have cancelled this and something we could have made. Okay, so I have to, if you focus on this particular one, I have to somehow get rid of, I have to somehow replace it with Vx. How to do that? How to do that? Well, one more thing is there. See, the speed is going to remain constant. All the time the speed is going to remain constant. The speed is neither going to increase nor decrease. Okay, let me write it here. Speed V, which means magnitude of velocity, is going to remain constant because it's moving in a pure magnetic field. So this also we have to make use of somehow. So how to make use of? Well, at any moment, for example, here, this velocity, the magnitude, that means speed, we can write as under root of Vx square plus Vy square. So let's try to do that here. So now a lot of mathematics will be there. So we know that V square is equal to Vx square plus Vy square. I want to get rid of this Vy. So I can make use of this. Okay. So I can say, come on, buddy. Yep. Sorry. So I can say कि Vy here is equal to under root of V square minus Vx square. And then you can put it in this equation. So we get Vx dVx by dx is equal to minus lambda. And instead of Vy, I'm going to write this. So you get under root V square minus Vx square and divided by this x. Okay. Now at least we have got a good and decent differential equation, because now the Vy is gone. So how to do it? Well, I think now it's done. Now all these Vx's, see, there is Vx over here, there is dVx over here, and there is Vx over here. So all the Vx we can move on one side, and there is dx and x over here. So and all the x on one side, this is what we call variable separable form. So you'll have Vx dVx and divided by this one, I'm moving on this side, under root V square minus Vx square, and on this side you'll have lambda, and this dx will go in the numerator, so dx by x. And then finally time to put integration. Now, when in the beginning, what was the value of x? It was given to be x naught. See, in the beginning, look at this, at a distance x naught. So in the beginning, it was given, and in the diagram also I have shown, in the beginning, this was the starting position, x was x naught, and in the final position, x is xm. In the beginning, this velocity was purely along x-axis. So I can make use of that fact. In the beginning, the x component was this. Should I write minus vx because it is purely along this? Maybe. Yeah. Or have I already taken care of that minus? I think I have already taken care of that minus. So I'm going to simply write Vx. And when x becomes xm, xm means x min. Okay. Then what is the Vx component? It becomes 0. All right. So how to do this integration is pretty simple. This integration of dx by x is ln x. We all know that. How to do this integration? Well, this is also simple. This is also simple. For a JEE student, these are like child's play. So what I'll do is I'm going to assume this thing as some other variable. So let v square minus vx square be some other variable called z. Better, I'm going to assume it to be z square. Now the derivative, v is speed, which is constant. So this speed ka derivative will be 0 minus vx ka derivative will be 2vx, okay, and dvx. And the derivative of z square will be 2z dz. Got it? So see, you get, this 2 also getting cancelled. This 2 is also getting cancelled. So you get vx dvx is equal to minus z dz. Okay, this minus sign is there. That's why I'm writing minus here. Now, here, so this vx dvx is there. So in place of that, I can write minus z dz, and this under root of this thing we had assumed z square. That's why we have assumed it to be z square, because it would be easier. I mean, yes, you can assume it to be z also. That also will work. So z square ka under root will simply become z is equal to minus lambda, and here you'll have ln x, and we have to put limit x naught to x. Okay, this z is getting cancelled. So what do we get? So we get minus dz, which means z. Okay, and z we had assumed it to be this, so let's put that. So v square under root because minus vx square is equal to minus lambda ln x by x naught. Now remember, this vx is a decreasing function. Just a sec. Yep. Vx is a decreasing function. All right. Yes. So are we getting a decreasing function? This minus is getting cancelled. Okay, students. So after spending few minutes, I understood that there is a small mistake somewhere creeped in. Okay, because of that, this minus was a big problem here. Okay, I had to spend few minutes to understand this mathematical error. This mathematics creates a big problem. Okay, sometimes I hate that. So I'll tell you the problem. See, otherwise there is going to be a negative error problem. See, the problem is I'll tell you where is the problem. The problem is literally here. Here is the problem. Why is here a problem? See, as per if you go simply logic by step, there doesn't seem to be any problem, because ax, we know it can be written like this, v dv by ds, and this minus is there, etc., etc. Everything looks perfect. Everything looks perfect. But there is a mistake. Here itself there is a mistake. That mistake is extremely difficult to understand. See, uh, let me take a space here. See, whenever we write a derivative, we know that, for example, suppose y is a function of x, and if it is an increasing function, okay, that means if x increases and suppose y also increases, then dy by dx must be a positive number. Okay, and if x increases and y decreases, then dy by dx must be a negative number, because the slope will be negative. What if x decreases and y also decreases? Okay, then actually it's an increasing function, because x is decreasing, y is decreasing. So so in that case, what should be dy by dx? Should it be negative or positive? It should be positive, because this is same as this. See, x increases, y increases. So if x decreases, y decreases. So dy by dx must be a positive thing. Now if you come back to our equation, just a sec, please see this equation. Where was I? Yes, this equation. Mathematically, you can't find any error. You can't find any error. You have to use a lot of thinking to understand there is error. See, as the particle is moving this way, here is this wire. As the particle is moving this way, this x is decreasing. X is decreasing. Perfect. What about the velocity x component? See, this is the velocity. This was the velocity in the beginning. Now the velocity is this. Overall, the velocity speed is not changing, but its x coordinate must be decreasing. Sorry, not x coordinate. What am I saying? X component must be decreasing. So Vx, which is the x component of the velocity, must be decreasing, and x is also decreasing. So you see, in this one, x is decreasing and Vx is decreasing. Both are decreasing. So how can there be a negative sign on this side? There should not be, even though mathematically it will always come. I mean, when you write these equations, you will get that, but you have to be alert enough. Like I was not alert there, but you have to be alert enough to say that this negative is not possible, and the reason is simple. As x is decreasing, okay, let me go back to this diagram. See here, as the particle is moving from here to here, its x coordinate is decreasing. That is perfectly all right, and the x component of this velocity is also decreasing, because the velocity is getting tilted, and finally when it reaches here, the x component of the velocity becomes 0. We already knew that. We had put that in limit. So as x is decreasing, Vx is decreasing, so this negative is a problem. So we have to introduce one more negative sign. Okay, introduce one more negative sign to make it positive. You have to make it positive. Okay, one more negative sign. One more. Okay, I'm not writing everything here. So the point is, you have to make it positive. Only then you can do this, perform this integration. Okay, so let me continue with the work, because the work was almost done. Here we had really got stuck here. All right. So initial velocity was v naught, and final velocity of this Vx component will be 0, and we had already done this integration. So this integration will be yes, what was it? Minus of Vx dx I can write as z dz, and this minus is because of this minus, right? And divided by z is equal to lambda ln x, and the limit is x naught to xm. All right, this z got cancelled. Sorry, here we had dz. Integration of dz is z. Okay, and here itself, let me replace the value of z, because z we had assumed to be this. So z will be under root v square minus vx square, and now we have to put the limit of vx. Vx initially was v. Again, there is no need to call it v naught. There is no need to call it v naught, because it was not v naught in the question if you read it again. And finally this vx will become 0, and here you'll have ln, and upper limit minus lower limit means xm by x naught. Okay, see, this minus should not have been there. This minus, we have to make it positive. Only then we can perform this integration, and I told you the reason. Okay, so let me get rid of this part. Yep, so you will get minus, put this limit vx equal to 0, so under root v square minus 0 square minus under root v square minus v square, because this limit is v, is equal to lambda. And lambda also, now I can put the value of lambda. What was lambda? Do you remember? I also don't remember. See, q mu naught I by 2 pi m. This is what we had called it, lambda. Q mu naught I by 2 pi m. So q mu naught I by 2 pi m was lambda, and ln xm means minimum x. Okay, that's what we are supposed to find. So here this is nothing but v minus v, because you see this will become 0, is equal to this. Should I write it again? Okay, q mu naught I by 2 pi m ln xm by x naught Now move it on this side and get rid of ln, so you'll get e to the power minus 2 pi mv divided by q mu naught I is equal to xm by x naught. So from here you get xm as x naught e to the power minus 2 pi mv divided by q mu naught I. This is your final answer. This is the minimum separation between the charge and the wire. Okay, so this charge will move, and this will be the minimum, because after that it will move, it will go like this, so this x will again start increasing. Okay, that's it for this question.